Welcome back. This is 6.1.3. We'll now study DTFS from a linear algebra perspective. We'll study the synthesis equation. That means we want to construct xn from ck. This is the synthesis equation. So basically it says that to construct xn, we use from c0 to c of n minus 1. That's all we need to do. And we multiply with this complex exponential, and now we'll study what this complex exponential means and why this equation can be viewed from the linear algebra perspective. Now, because the signal is periodic, small n only goes to n minus 1. What happens at n to n, 2n, and so on is because when you use from n at 2n, the equation remains the same. Alright, so now let's deal with x0 to xn minus 1. We now write the notations as a column factor with n elements, big N elements, x0, x1 until xn minus 1. Ck are scalars, they are complex scalars, magnitude and phase, but we can just simply write it as scalars now. C0 represents is a complex number, or I should say ck's are complex numbers. Now we are now going to write what does c0 multiplied by this means. So what we need to do is we substitute k equals to 0 here, and now we are going to change different values of n. So this is n equals to 0, this is n equals to 1, this is n equals to 2, until n equals to, in this example, is n minus 1. Now, if this e to the power of 2 pi over big N, what is big N? Let's, for example, big N is equals to 8, as in our previous examples. So it is 2 pi divided by capital 8, which is pi divided by 4. Pi divided by 4 times k, which is always 0 for the first guy. So this is I to the power of 0. So therefore, the first column is all values 1 because it is nothing but e I pi over 4 times k equals to 0 times different n. And therefore, regardless of different n, since k is equal to 0, we end up with the column of 1s. What about the second column? The second column, we call it B1, associating with C1. So I'll highlight, now k is equals to 1. Big N remains as 8. So this is still pi over 4. And small n will go from 0 to, in this case, 7. So this first guy is e times I, pi over 4 times k is now 1 times 0. That's why he's 1. The second guy is nothing but e times I, pi over 4 times 1 times 1. So that's why he becomes ei pi over 4. This guy times 2. That's why it's pi over 4 times 2 is pi over 2. I mean, we are using n equals to 8 now. So you can now work out different columns and different values. And once you have worked that out, you realize that I now can represent this equation as a vector matrix multiplication. So what do we have? This is x is equals to b times c, where x is this vector x, b is, I put all these columns together into what do you call that? The matrix B. And then the coefficient c's, I put it here. So this guy is c0, c1 until cn minus 1. Now let us study how to solve for x equals to bc. X equals to bc if b is this matrix here. If b is invertible, therefore c is equals to b minus 1 x. Yeah, since b times b minus 1 times b equals to identity. So from a linear algebra perspective, it is now obvious what C is. C uses a b minus 1 matrix to transform x into the coefficients. To reconstruct x, we use C times the b matrix. B and b minus 1 matrix are nothing but inverse of each other. So Fourier analysis from this perspective is a change of basis. Thank you.